All right, I just wanted to start with a quick recap of the investigation that we started or finished yesterday in class. Notice that we did discuss or see all of these different power-up type of situations or scenarios that we would use to find the antiderivative of x to some power. But what's kind of been lurking in the background is the fact that there is one power of x that we can't power up, and that's x to the negative first, to find its antiderivative, just because when we divide by that new power 0, we get something that's undefined. So the investigation was to start to think about like what kind of function that is that requires the integral of 1 over x. And as we saw, we got this table of values, and we saw all the values of x that were given as sort of like paired up as an input value of x and then its reciprocal. And what we noticed about those values is when we inputted a number like 2 and its reciprocal, it actually outputs the exact opposite in value. Same number, but exact opposite. And so we can start to kind of see that we can build this relationship of when I plugged in positive 1/2, I get the opposite of when I plugged in positive 2. When I plugged in positive 3, I get the opposite of when I plugged in positive 1/3. And then the same thing for any value of when I plug in 1 over a, I get the opposite of when I plug in positive a. So that's kind of the first little feature that we're seeing from that first task. In the second feature, we're noticing that that the graph that we're trying to accumulate to actually has a vertical asymptote at x is equal to 0. So if we wanted to try to accumulate all the way back to 0, we can't do that. It's going to give us an undefined quantity just because we can't accumulate to no definite endpoint. Doesn't make sense to stop where you're not allowed to actually reach on the graph. So then if we want to look at what the limit is as x approaches 0 on that right-hand side, we can see that the accumulation comes more and more negative, and so then it starts to approach that negative infinity. And then we started to think about, well, what actually is going to make this, what value of x will make this actually equal the number 1? Now, that's just something that I chose kind of to force your hand in trying to think about this, but you guys chose some different ways of working with this, either graphically or using the definite integral, but 2.7 was a pretty good estimate, but really 2.718 is even a better estimate, and the mathematical constant that we have that actually is the closest to that value, 2.7, 2.72, 2.718, is E, this like mythical constant E. Then when we finally kind of put all this together, where we plot the points from the table on the previous graph, and we look at the domain and the range and how it's increasing, or concavity and the intercepts and the asymptotes, we get this shape, which hopefully looks pretty familiar, right? And now finally at the very, very end, we're going to put it all together, and it looks like with all of the features that we saw, that when I input the reciprocals, I get the opposite value out. When I input 1, I get 0. Didn't really talk about that. That the limit as x is approaching 0 from the right is negative infinity. That when I plug in e, I get 1. And then the graph itself, it looks like the natural log function. And actually, that's exactly what this function is. It's just the integral definition of the natural log function. You can see a couple of extra notes here that I've put just to kind of reinforce the fact that, yep, this actually is the natural log function. The very first property is a property that works for all logarithms, but the fact that f of e turns out to be 1 is what kind of sealed the deal to say that this is actually the natural log function. And what that led us to is that we now have this integral relationship that tells us that if I wanted to find the derivative of a natural log function, it would be like finding the derivative of an integral from 1 to x of 1 over t dt, and that's just 1 over x. So now we're going to use that rule. Okay? So just kind of writing it at the top of our paper so that we can see it, that this is actually just the natural log function. So I want to take the derivative of that. We can use that fundamental theorem of calculus to say, just dump and derive that f prime of x is just 1 over x. But that just means that that's the derivative of the natural log of x. And so if I wanted to actually include the chain rule in this, if it wasn't just the natural log of x, then the derivative with respect to x of the natural log of u is equal to the natural log of u times du dx. And so that's the rule that we're going to use for all of our future logarithmic expressions. Okay? So here's our first example. We've got the derivative of natural log of 2x, and so notice that I quickly just said that that's going to be, I'm basically saying that u is equal to 2x, so that's 1 over 2x times 2, which can easily simplify to just 1 over x. I'm just curious by the fact that I just got 1 over x for this function, but that's also the derivative of the natural log of x. Is it interesting that that's the same thing for just y is equal to the natural log of x? Well, not really when you think about the properties of logarithms. If I go back to that original function f and I think about the properties of logarithms, which is something that's in that prerequisite practice that's listed on the study guide, that if I take the natural log of 2 times x, that I can actually expand that and make it the natural log of 2 plus the natural log of x, which is really just a vertical shift of the natural log of x. So multiplying x by 2 does the same thing as shifting the natural log of x up by the natural log of 2. And so they have the same, so that they have the same derivative essentially because the vertical shift doesn't change it. Got a little bit ahead of myself. On the next one, we've got f prime of x is equal to, or f of x is equal to the natural log of x squared. But if I use the rule, it's just 1 over x squared times 2x, so 1 over u times the derivative of u with respect to x. And then, of course, that can be simplified to 2 over x. But now I'm looking at this one and kind of curious that it looks like that would be the same for y is equal to 2 times the natural log of x, because it's just 2 times 1 over x. But again, if I go back to that original function, notice that we've got another log property that says that we can just pull down the power on the x and have this new function that says g of x is equal to 2 times the natural log of x. And notice that that actually does have the same derivative. Now, don't be confused. These are not actually the exact same function. They just have the same properties for the values of x that we can plug into them. If I think about the graph of what g looks like, 2 times the natural log of x, that's still just the natural log function with a vertical stretch of 2, so it has that same shape, but I can only plug in positive values. But if I use the original function f, where it's the natural log of x squared, since I'm squaring the x before I take the natural log, it's actually okay to plug in negative values. We would actually get sort of like back-to-back curves like that, and either positive or negative values are allowed. What the derivative means is just that these two things would be equal in value for the values of x that I could plug in for both of them. Notice that the right sides are essentially the same. It's just that the purple graph also has a left side. And notice that the left side of the purple graph is decreasing for any value of x that I plug in that's negative. And the derivative would also be negative, indicating that decreasing curve. Positive for increasing side, negative for the decreasing side. Don't get confused about what you're seeing with example 3. Now I put parentheses around the natural log, and then that's being squared. You cannot use the property that we used up above on number 3. Okay, this is actually a chain rule where the logarithm is the inner component of the composite function. So the first thing I would do is power down the 2, don't change the natural log, but then multiply by its derivative. So I can simplify that to just say 2 times the natural log all over x. Okay. Last couple of questions there. Hey. Last couple of questions. If we notice this first one that we have here, looks like we're going to have to use the product rule because it's x times the natural log of x. So I'm going to take the derivative of the first, multiply it by the second, and then plus the first times the derivative of the second. And then that can be simplified just to the natural log of x plus 1. Just be aware that all the things that we've used before still apply now. The next one looks like it can be a little bit confusing. You can see kind of what I'm doing here. This would be a pretty nasty derivative to take if I just jumped in and try to take the derivative as is using the chain rule. So I'm going to use those properties that we know from pre-calculus where we can expand this logarithmic expression to simplify the arguments. And the first property that I'm going to use is just to take this ratio, this fraction, and split it up by subtracting. And then I'm also going to pull both of those exponents on the arguments down to the front. So we get 3 times the natural log of x minus 1/2 times the natural log of the quantity 2x plus 1. This is going to be a much easier derivative to take because now I'm just going to get 3 times the derivative of 1, the derivative which is 1 over x, minus 1/2 times the derivative of 1 over 2x times 2 for the chain rule. Sorry that came out so quickly. Okay, so then we've got that as our final answer. That's perfectly acceptable. You might see that where they've actually combined and gotten a common denominator and combined it into one fraction. Totally unnecessary, but just be aware that that might happen. In our last example here, we are trying to find dy dx, and notice that this is an implicitly defined equation, so we need to use implicit differentiation. If I start off and just find the derivative with respect to x, notice that I've got the natural log of xy. That would require not just the chain rule with the natural log expression, but also the product rule to find the derivative of what's inside, which I don't think that's too difficult to actually do, and then I can find the rest of that derivative. The thing is that the algebra after this step is kind of crazy, trying to solve for dy dx here. So I'm actually going to scrap that and use that property that we used up above to expand the natural log of xy to the natural log of x plus the natural log of y. Notice this is now back to the original expression. That's not a derivative anymore. Now I'm going to take the derivative of that, much easier to take. So we got 1 over x plus 1 over y dy plus 5 dy minus 3 is equal to 0. Much easier to get dy dx all by itself by keeping those terms, factoring it out, and then solving by dividing by that expression. Remember, guys, we always say simplify for our convenience. This is completely acceptable to keep, but you are definitely going to see this where they've simplified the complex fraction. So I would multiply top and bottom by the common denominator, which is x times y, and I'd end up getting 3xy minus y all over x plus 5xy. All right, I hope you enjoyed the video. Can't wait to see you guys on Monday.